Hello friends, welcome to this discussion. We are going to continue with simple harmonic motions part 2. So here we are going to simply continue where we ended from in part 1. So in this one we're going to just cover characteristics of a simple harmonic motion. We want to look at what is involved when you're looking at simple harmonic motions. Okay, so that's in our earlier discussion looked at the differential equation of a simple harmonic motion. So in this discussion, we're just continuing from where we ended from. So this is the form in which the differential equation was given in. Okay, like that. So this was our form. So in this discussion, we'll just continue. That is with looking at the characteristics of a simple harmonic motion. So under characteristics, we have things like the amplitude, we have things like the angular frequency, we have things like the period, the frequency, and also not forgetting the phase constant. So these are things that we have. Now before that, we need to acknowledge that for this to happen, we need the equation of displacement. So this equation of displacement is simply a function that is dependent on time as our variable. So mean that the inputs in this case are t, which is the time, and the output simply gives us the y, which is our function. So the amplitude, angular frequency, the period, the frequency, the phase constant, these are simply characteristics that we want to look at in this discussion. Okay, so before that, let us acknowledge the equation of the equation of displacement. So y is equals to, that is a sine open angular frequency t plus the phase. This is for vertical simple harmonic motions. That is for vertical motions. Then in a case where the kind of motion is horizontal, meaning that our equation will be x equal to a cos angular frequency t plus the phase. So this is just for the horizontal simple harmonic motions. So the a that we have in both equations for the vertical and the horizontal simply stands for the amplitude. The w, which is omega, there stands for the angular frequency and all that. So let's look at the amplitude. Now amplitude is length, which is simply abbreviated by a capital letter A. Now this same amplitude simply just talks about the maximum displacement from the mean position to the extreme points. So as not to say, for a simple harmonic motion, an object will move from the mean position to the extremities. So this amplitude just gives us the maximum displacement of an object from its from its mean position. Now since it is amplitude, which is length, meaning that the units that we use to quantify this amplitude are simply meters, unless of other provisions, but the units that just required to use are meters. Now the next one that we're going to look at is simply the angular frequency. So angular frequency will be the next one to be discussed, which is given by the symbol small omega, like that. So angular frequency is simply the rate of change of the phase with respect to time. So here you're looking at how the phase is changing with respect to time. Now by phase we simply mean that a parameter that simply gives us the position of an object in this motion. So it gives us the position of an object at an instant. Now if you're looking at the rate of change of these same positions, or that we have at an instance, what you get is simply the angular frequency. And not only that, it can also be defined as how quick it takes for an object that is undergoing a simple harmonic motion to simply complete a circle. So if it moves from point A going to the mean position B, and then going further to another extreme point which is C, and then back to the mean position and A, that has completed a circle. So how quick it would take for it to complete one full oscillation or circle is what we refer to as the angular frequency. Now this angular frequency can be calculated by simply using equations. So the angular frequency can be calculated by the same formula that we used for the angular frequency square that we substituted in our differential equation for a simple harmonic motion. So the equation is omega, which simply represents the same angular frequency, is simply said to be equal to the root of k over m. Okay, so it is given as, so look at the formula, is just one. You can use all this. So the equation is the angular frequency is simply equal to the root of k over m, like that. Okay, then the other way in which you can express this one is simply by saying that the angular frequency is equal to 2 pi multiplied by the frequency. Or if not this one, we can also look at the third one where I say that the angular frequency is simply equal to 2 pi over the period, which the period is simply time taken for an object to complete one full circle. So you can say that 2 pi over the period, like that. So this is simply how we measure the amount of angular frequency, that is by use of the formulas. So the next component we're looking at is simply the period, since we've looked at the amplitude and the angular frequency. So period is simply the time. Now time in this case is simply abbreviated by a capital T. So this is simply the time that an object takes to complete one full circle. So that's what we refer to as the period, the time taken for an object to complete one full circle. Now since it is time, meaning that the units that we can use to measure this one are seconds. Okay, like that. So simply the time taken for an object to complete one full circle or oscillation. So like what we did with angular frequency, we can also quantify this by use of the formula. So it will be equals to 2 pi over the angular frequency. But remember that angular frequency is equals to the root of k over m, so it will be 2 equals to 2 pi over the root of k over m, since that's also another expression for the angular frequency, which is equals to t equals to 2 pi. We can open brackets, then you say what you have for the angular frequency raised to the power -1. That's from the laws of indices. This is mathematical, so it will be equals to 2 pi. So open, so it will just change, m will go on top, then k down, because of the negative exponent, -1, that we have there. So this is also an expression of a period. This is how we can simply express period, so depending on what we've been given in the question. So we look at frequency now. So what is frequency? So frequency in most cases is given by a symbol small letter f, and this simply talks about how many number of oscillations has been completed in a unit time, like how many circles have an object completed in a unit time or in a period of time. So it is measured in hertz. So hertz are the units that we use to simply measure frequency, which is symbolized as Hz, H capital then Z small. So this one also can be quantified by use of formulae. So we can use formulas to simply quantify the frequency. So the frequency is equals to the 1 over the period. So it's simply 1 over the period. So it's simply the events of a period. So it means that we can substitute where there is a period with this is 2 pi. So we can say 2 pi over the angular frequency, of which this can simply give us the frequency to be equal to the angular frequency will go on top divided by 2 pi, like that. So we know that angular frequency is the same as k over m, so we can say that the frequency in this case will be equal to 1 over 2 pi multiplied by the root of k over m. So this is what we get. So these are some of the formulas that we can use when we are simply calculating our frequency for a simple harmonic motion. Now from there we'll go to the last part of this discussion, which is the phase. So the phase, like I had earlier alluded to say that, is simply a parameter that helps us to know the position of an object in the motion at an instance. So don't say an object moving in a periodic manner where it is repeating the same motion. So when you talk about the position at an instant or at any point in the motion, what we simply get is the phase constant. Okay, so what we'll have there, we'll look at the position of an object at an instance in the motion is what we refer to as the phase constant. And that's not to say, for a simple harmonic motion, we have the mean position. So mean that the phase constant at the mean position, at that particular position, is simply referred to as the initial phase. And at that point, particularly at the mean position, the phase is given as 0. So mean that the phase is given as 0. So it is given using a symbol, the phase, then subscript naught, mean that the phase subscript naught, which is phi as a symbol which is used, then you put the subscript over a 0, so that simply represents the initial phase, and this same initial phase in this case is equal to 0. So since this gives us a 0, it therefore means that going back to our equation for the displacement, we simply get a 0 where we have the phase. So this will give us a transformation of our equation, so meaning that our equation of displacement, which is with respect to time, will be equal to a sine the angular frequency t plus a 0, which is just the same as saying y equal to a sine then the angular frequency t. So this is where we're going to end from this.